Okay, so these are the summaries for quantum number of electron in atoms. So for quantum principal symbol is n. It has positive integer 1 to 3, and this is determine the orbital energy, the size. Whereas the level is it 1, 2, 3, 4. Okay, for angular momentum, the symbol is L. Okay, the integers from 0 to -1 is determine the orbital shape, either S, P, D, okay, or F. Alright, so is according to orbital 0, 1, 2, 3. Okay, and then we have M, magnetic. Okay, ML, this is refer back to L. The integer from minus L to positive L, this is determine the orbital orientation, and also spin, okay, positive half and negative half. This is determine the direction of. Okay, so to be more understand, we can put into this list. If n is equal to 1, if n is equal to 1, so L is 0. This is because n minus 1, okay, L to 0, and ML is according to L, so it's going to be 0. So 0, normally 1 orientation for, this is orbital n1, so this is level n1, okay, and S is for 0. Okay, so you put 1s. So number of orbital is reflected here, orbital designation. So number of orbital is 1. If you have level 2 and equal to 2, you're going to have 2l. Okay, 0 or 1. So 0, this is reflected here, so 0. And then 1, ml is reflected here. Okay, so it could be -1, 0, and positive 1. So we start with 2, orientation, orbital designation at orbital 2. So for 0 is S. For 3, this one, 1, 2, 3, ml is equal to 3. So that would be belong to orbital P, 2P, which is number of orbital is 3. Number of orbital, you look at here, 3 or this one. Okay. And then for 3, n equal to 3, L is 0, 1, 2. For 0, ml is 0. For L is 1, so it has negative 1, 0, or positive 1. So it's just, it has 3 orbital, and which level at 3, because this is level 3, n is equal to 3, so S is 0, P is 3. And then for 2, L is equal to 2, you have 5 ml. -2, -1, 0, positive 1, positive 2. That will give 3D. And number of orbital is 5. Refer to here, or 3D orbital is 5. Okay, so this is S orbital. P orbital, you have 3 P orbital. S orbital normally reflect to n equal to 0. L equal to 0. So sorry, this is L equal to 1. Okay. And then D orbital is reflect to 5. 5 orbital. So when you see this one, how many orbital is allowed for n is equal to 3? It's being given n is equal to 3. How many orbital allow? Okay, for n orbital, for n is equal to 3, L is equal to 0, 1, 2. Okay, and for L, you do it one by one. For L0, M is 0. For L1, ML is equal to -1, 0, positive 1. For L is equal to 2. So M is equal to -2, -1, 0, 1, and plus 1. You have to do this one by one. So by doing this, okay, so how many orbital are allowed in n is equal to 3? So there are 9 m. 1, 2, 3, 4, 5, 6, 7, 5, 6, 7, 8, and 9. So 9 m value, and therefore 9 orbital with n is equal to 3. Okay. Give the name, magnetic number, magnetic quantum number, and number of orbital for each sublevel for each the following number. N is equal to 3, L is equal to 2. So you must know how many number of orbitals. So you have to do one by one. N equal to 3, do it one by one. You can do the table like this as well. N is equal to 3, L is equal to 2. Right, so the sublevel is 3D. Alright, and that one. Okay, orbital position is 5. Alright. Okay, and then next, okay, n is equal to 2, l is equal to 0, so sub-label name is 2s, because 0 represent s, okay, 2 represent orbital d, then this one will be 0, so only one electron can be fit there. And for c, n is equal to 5, 1, so 2p. We always remember that 0 is s, 1 is p, 2 is d, alright. So so p akan ada 3 electron, minus 1, 0, minus 1, positive 1, so it will be 3 number of orbital, 4 and 3, so 4, 3 is represented f, represented f, so f would be 7 number orbital. So we go with arrangement of electron. This is the important rule. We have normally 3 rules for assigning electrons. First, following the Aufbau principle. Number 2, following the Pauli exclusion principle. And number 3, following the Hans rules. So Aufbau principle, the electron fill the lowest energy sublevel subshell first before moving up to the next level. So Aufbau means building up. So you must follow levels. Lowest level must be filled in first before going up. So 1s must come first, then 2s come later, 2p come later, followed by 3s. 3s goes to 3p and 4s, then followed by 3d, 4p, 5s, 5d, and so on. Okay, so this is the way how it being called. So 3p always lower than 4s. Okay, this one 4s is a bit higher lah. Okay, this one 3p has lower number compared to 4s, and 4s has lower number from 3d. 3d it has highest orbital compared to 4s, because 3d you have your orbital is fulfilled, everything is full here compared to 4s here. So this is the energy level. You can see 1s is lowest, 2s is second lowest, 2p followed by 3s, 3p, and 4s must come first. 3d is a bit higher than 4s, then followed by 4p, 5p, and so on. Okay, so number of electron must follow n, l, m as just now. So n, l represent the s, p, d, f. Okay, right. So this is how we write configuration: 1s2, 2s2, 2p6, 3s1. So this letter tell you the subshell. What is the subshell? While this number tell you the number of electron in the subshell. Is it full or not? So p normally fully occupied, 6 electron will be fully occupied here. While this number, the biggest one at in front, it tell you the main level of. Okay. Pauli exclusion principle, the maximum 2 electrons can occupy each orbital. It's like in a room, only 2 people can occupy a room, for example. Okay, right. So electron normally it has clockwise or anti-clockwise spin here. Okay, so Hans rule is state that when entering the orbital of identical energy, electron initially occupy them singly and with the same spin, meaning that they are in parallel space. Then only there can be subsequently occupied. Then only we start pairing them. So how to do it? You have to fill in single first. 1. Let's say you have 4 electrons. How to fill this orbital? 1, 2, 3. You must fill in all the room available first. Then only you couple up 4. Okay, you cannot put in like this. 1, 2, 1, 2. That is wrong because you're going to have one empty orbital at the back. So example, sodium has 11 electron. How do we write the electron configuration? So it has 1s2, 2s2, 2p3, 2p, and 3s. How to fill the electron? 1, 2, orbital s settle, and then 2s, 1, 2 settle, and then 2p, 1, 2, 3, and then couple up 4, 5, 6, then only you settle, and then the rest you put here 1. Okay, so for electron rotation, you must know how to write in condensed or expanded. In condensed, 1s2, 2s2, 2p6, 3s1, like this. You write like this. While in expanded, you expand everything. 1s2, 2s2, 2px2, 2py2, 2pz2, because 2p have these three orientation, x, y, z, and then 3s1. So that's how we will write the expanded version. Okay, so ions and isoelectronic configuration, we also can write like this. Okay, if you have aluminium without the charge, so aluminium has 10, 12, 11. Okay, 11, 12, 13, sorry, 10, 12, 13, 13 of electrons. So how you write it? 1s2, 2s2, 2p6, 3s2, 2p1. But if you have 3 charge here, charge plus here, meaning that you have to subtract 3 electron. Normally we reduce the one that at the back. So we withdraw this one, 3p1 and 3s2 will be withdraw. So what remaining is only 1s2, 2s2, 2p6. For also electronic, it means different species having the same electron configuration. It's like O2 minus. Okay, O2 minus, oxygen is supposed to be 12, right? Right. So when you have 2 minus, it means that you're going to add 2 more to you. Okay. Oxygen is 14. Oxygen berapa? 12. Yes, 12. So you're gonna this should be exclude, okay, exclude plus 2 plus 2 here should be 2p 3s2 at the end. Okay, this is the same, right? This is the same. Look at this one. This is how we write the partial orbital diagram. Okay, first thing first, we have to fill in single and then couple up, and then if you have more electron, then only you goes to another orbital, right? And then you have more left, you fill in the rest until all the room are occupied, then only you couple up. Okay, and then only you couple up the next, then only you couple up the rest. Okay, so if you have 18 electron, we can put in bracket 10, 1s2, 2s2, 2p6, 10. The rest, what is remaining? The rest 3s2, 3p6, or you may represent with the what is our inert gas that we have before argon. Okay, before argon, you can see in the periodic table, argon is seated on which periodic table? Alright, so the gas before argon is neon. So neon is represent 10 because argon is 18. Neon is 10, and then the rest is 3s2, 3p6. Alright. So this is another electron configuration where we can write, for example, chromium. Chromium is 24, right? 10, 16, 18. 19, yes, 24. Okay, you may write the full configuration like this, or you may represent the argon gas. Okay, you may represent with the gas that is inert gas before it. Chromium, where is position of chromium? Look at what is above it in the periodic table is argon. Argon is 18. Okay, 18, 19, 24. You may represent like this. So you just draw for 3D, 3D 5, 1, 2, 3, 4, 5, 4 as 1 like this. So it's singly, and all are occupied. Okay, all having the occupied electron. But you have copper. Copper, for example, is 10, 12, 18, 19, 39. Okay, 39, 29, 29. Argon is 18, 20, 30. Is it 30? 10, 12, 18, 28, 29. Okay, or you can do like this. Argon is 18, 19, 29. Okay, so 29. So argon represent argon 3D10, 4s1. So 3D all are being occupied, where you singly put in according to the Han theory and Pauli, and okay, and then you couple up. Okay, then only for S. Okay. Okay, so this is configuration for period number 4. It's simple. Okay, you can start with argon, 4s1, 4s2, and so on. Then this one, same thing. Configuration for Sn minus n1. So Sn minus meaning 16 plus 2. Okay, electrons. So 18. 18 electron. This is how you write the electron configuration. Or 28, you may, if you have plus, so meaning it's minus 2, become 26. So this is the electron configuration. If you have plus 3, means you have to minus 3. So this is the electron configuration. Okay. Alright. So let's stop here first because we are running out of time. Okay, so this one, try this exercise. Okay, try this problem. Find for potassium, Z is given. Okay, atomic number is given. That's the value. So find the solution. Okay, full configuration and also condensed configuration. And then same thing. What is dimagnetic and also paramagnetic? Okay, paramagnetic meaning that the content need unpaired spin and they are attracted by the magnet, while this is unpaired, so single. Dimagnetic, it means that it do not have any unpaired spin, but they are paired, they are anti-parallel to each other, okay, like this or like this. Okay, so paramagnetics, they are single unpaired electron which is fill the orbital like 2p2, right? Or dimagnetic, you have 2p6, so all are paired here. So draw this one. Predict whether ion is paramagnetic or dimagnetic solution. Right, so